Hello engineers, and welcome to 2.1.5 Moments, Part 2. We're going to be finishing up the lecture on moments. We'll do a little bit of a review of what we covered, and then we'll finish on with the last two example problems that we've got for today. So remember, a moment that we talked about last time, it's the force perpendicular times the distance. So you take whatever force you're pushing and you multiply, and make sure that that force is perpendicular. You multiply by the distance. We have positive and negative torques, force times distance. You can use foot-pounds. We can use inch-pounds. When you're pushing at it, remember it's always the perpendicular distance. If you are pushing at an angle, like this one was, you have to make sure that you find the component of that force that is perpendicular to the lever arm. And then we talked about equilibrium and how that means different things. It means that you can't, anything pulling left equals everything pulling right. So the sum of forces left and right equals 0. The sum of forces up and down equals 0. And the sum of moments. And that's where we did our little teddy bear problem, where we said that this positive moment is going to equal this negative moment. So when you add those two moments together, this force, 25, times the distance 4, 100, is equal to 40 times x, and that's a negative moment. Solve that and you get 2.5 for your distance. We're going to take off today, kind of going down this road with two more example problems. So we've got a loaded beam here, A and B, and it looks like there's a present at 3 feet in. And the question's going to be, how much force is on support A and how much force is on support B? I think what we can do I'm just going to step back. Now, if this was simply supported, and it'd be nice if they would have done this. I would have liked that if this was and then this here was a roller. So if this was a pin and this was a roller. So if it's a pin, that means that there's a supporting force, the force at B in the x direction, and that pin is also preventing it from going to the left and right. The force at B in the x direction. Oh shoot, this should be a y, this one here. Because there are no left and right forces here, this is going to equal 0. So there's actually, this goes away. There's no force. And then the roller is supporting the force at A in the y direction. So we're charged with figuring out how much force is at A in the y direction and how much force is at B in the y direction. So here's where we're going to use that the sum of moments is equal to 0. So what I'm going to do is I'm going to pick a place to put a pivot. Put your pivot at one of your unknowns. You're totally within your rights to take and put your pivot right here. But it's going to be a lot easier for you mathematically if you take and you put a pivot right here at one of the unknowns. So here's what I mean by that, and here's how this pivot helps us. So this force right here, this 35 pounds, this 35 pounds is cranking it this direction. Right? So if here's the pivot, it's going to crank it around that pivot in this direction. So is this a positive moment or is this a negative moment? This is a positive moment. So I'm going to change this to red. And we can figure out that moment because it's the force, 35, times the distance, 7. Now, that means that this right here is 7. You can figure that out, 10 minus 3. So 35 times 7 210 plus 35, 245 foot-pounds. Now, this force over here, this force A at y, this is turning it in this direction. Is this a positive torque or a negative torque? This is a negative torque. So I'm going to change it to blue. And the moment here is the force, which we don't know, times the distance, 10 feet. It's 10 feet all the way over there. So here's how this moments, they add up to 0, works in our favor to help us figure out the forces. If we add up all the moments, those are going to be equal to 0. So we've got a positive moment, a positive 245, right? We found that before. And then we have a negative moment, a negative FAY times 10 equals 0. So move this 245 over, a negative force of A in the y direction times 10 equals negative 245. So then divide by negative 10. The force of A in the y direction. So this support over here equals 24.5 pounds. And we use that moment to figure that out. Now, we can also use the fact that all of the forces in the y direction is 0. Everything pulling down equals everything pulling up. Check it out. We've got some downward forces right here, a negative 35. And we've got an upward force right here, 24.5. And we have an upward force right here, FBY. So, negative 35 plus 25 is like a negative 10. So it's negative 10.5. So this FBY turns out to be 10.5. So it makes sense that this present over here, since it's so close to A, there's going to be more force on A, 24.5. B's got half the amount of force on it, 10.5. And we did that, first of all, by using the fact that all of the moments are going to be equal to 0. And then we use the fact that everything pulling down equals everything pulling up. All the forces up and down equal 0. Here's how we're using equilibrium to help us solve for these. Let's try another one. So here we've got a truss, and there's two forces acting on this truss. And you can see that this is a roller. So it's got that one reaction force, and this was a pin. So it's got two reaction forces, one in the x direction and one in the y direction. So we're going to use those three ideas that everything pulling left and right equals 0. Everything pulling up and down equals 0. Everything cranking clockwise equals everything cranking counterclockwise. The sum of all the moments equals 0. So let's use this first one here first. Everything pulling, so we've got a positive right here, a positive 500. So I'm going to say to the right is positive. A positive 500, and then we also have RAX. That's also a positive. The reaction force at A in the x direction. See how it's pulling? It's also pulling to the right. So we made that positive too. Watch what happens. So when I solve this, reaction force at A in the x direction, it equals negative 800. Sorry, I went ahead. if you end up with a force being negative, all that means is this, and it did. This turned out to be a negative number. It just means that you have to point your force in the opposite direction. This force is actually going this way at 500 pounds. And that makes sense. If you're pulling to the right with 500 pounds right here, then you have to pull to the left at 500 pounds. So there's my first one solved. Let's use a moment. So we're going to pick a place to put a pivot. And I'm going to make my pivot in blue. I'm going to put a pivot right here, because this is one of my unknowns, this reaction force at D in the y direction. So now I'm going to add up all my moments. So here is a moment. This force is causing a torque that direction. Is that positive or is that a negative torque? That is a positive torque because I'm going counterclockwise. So I'm going to turn it red. This torque, this force right here, this 500 pounds, this is cranking it clockwise. And clockwise is a negative torque. So I'm going to change that to blue for a negative torque. And now I've got a force over here. Sorry, that goes ahead sometimes. This reaction force at A, see how that's pushing up? I'm turning this direction. So that's also a negative torque. So I'm going to change that one to blue as well. My moments have to add up to 0. So my two negative torques have to equal my positive torque right here. So I think we can actually figure out what my torques are. This force, 500 times the distance. So 500 times 12 is 6,000 foot-pounds. So there's one of my torques. I've got another torque here. I don't know the force, the reaction force at A and the Y, but I do know the distance, and that's 32. Force times distance. And I know this one right here, it's 600 times the distance 8. So 600 times 8 is 4,800. So adding up my moments, I've got a positive 4,800. I've got a negative 6,000. And I've got a negative 32 times the reaction, and that's going to be equal to 0. So 4,800 minus 600, that's a negative 12. So then I take the negative 1,200, move it over, and I get negative 32 RAY. That's going to equal a positive 1,200. So the reaction force, A and the Y, 1,200 divided by negative 32. Boy, I can't do that one. That's the one I can't do in my head. 1,200 divided by negative 32, I get negative 37.5. So the reaction force at A in the Y direction is negative 37.5 pounds. And that's interesting. See how it's negative? That means that it's not pushing up like we thought. We had initially thought that this thing was pushing up, but really it is not. This thing is pulling down at 37.5. So here, so that's thing number 2. We figured out the reaction force at A and the X. This was 500. Now we figured out the reaction force at A and the Y. Now we have to figure out the reaction force at D in the Y direction. So we're going to use our last equation. Everything pulling up and down equals 0. So check this out. I've got a 37.5 and it's pulling down. Negative 37.5. This force is pulling down. This is getting really complicated. There's lots of arrows and things going around here. Maybe I'll try to simplify. I'll try to erase some things. I don't know why that keeps going forward on me. We don't need this torque. Get rid of that. Get rid of this. Get rid of this torque. Here, let's just try to simplify our drawing. We knew this was 37.5. We know that this is 500 going this way. Okay, so here's an up and down force, 37.5. Here's another one, negative 600. And we don't. And here's one. It's a positive reaction force at D in the y direction. Those are all our up and down. This is not an up and down force. This is pulling to the right, as is this one. This is pulling to the left. So those do not go here because of that. So negative 637.5 plus r dy equals 0. So I move that to their side. The reaction force at D in the y direction is 637.5. So this has to support 637.5 pounds. So there you've got it. And if you think about it, everything that's pulling down, 637.5, has to equal everything pulling up, 637.5. Everything pulling to the right, 500, has to equal everything pulling to the left, 500. And all the torques have to balance too. You can't just put random numbers. You can't just say that, oh, this is 600 and that's 0 over here. The torques have to be equal as well. So you had to use this to end up with our reaction force at A in the y direction. So, kind of some crazy stuff here. I hope that you're able to follow along. And we're flexing these three equations that everything pulling left and right is equal to 0. Everything pulling up and down is equal to 0. All the moments equal 0. And put your pivot at an unknown. So I put my pivot here at D. I could just as easily put my pivot over here at A and solve it a different way. Thanks a lot, and we'll talk to you later.